Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's jump right in. For, decades now, the big question, the one driving so much astronomy, has just been, are we alone?
It's fundamental, isn't it? The ultimate question, really.
And we found thousands of planets out there, exoplanets, since the 90s. But this new one, this super Earth, GJ251c, it's apparently less than 20 light years away. And researchers are calling it, quote, the best chance of finding life elsewhere in the near future.
That's a pretty bold claim.
It is bold, but there's solid reasoning behind it. It's generating a lot of excitement, and for good reason.
So today we're doing a deep dive into this. We've got the announcement details from Penn State researchers and their international team dated October 23, 2025. Our goal here is to really unpack this for you.
Get past the headline.
Exactly. Not just what they found, but how they found it. Because apparently this took, 2 decades of data?
Over 20 years, yes. A massive effort.
And we want to understand why this planet, GJ251c, is suddenly the prime target, the one everyone's focusing on for habitability.
It hits a kind of trifecta. Okay, let's start with the basics then. The planet itself, GJ251c, it orbits a star called GJ251.
A nearby M-dwarf star. Relatively cool compared to our sun.
And it's a super-Earth. What does that mean in practice? The data says it's almost 4 times the mass of Earth.
That's the estimate, yes. Around 4 Earth masses. And crucially, the data strongly suggests it's rocky. Like Earth, Mars, or Venus, not a gas giant.
Right. Now, we've found other super-Earths, haven't we? Finding a big rocky planet isn't entirely new.
No, not in itself. We know of quite a few.
So why all the buzz about this one? With over 5,000 exoplanets cataloged, why does GJ251c stand out so dramatically?
Well, like I said, it's this combination of factors that really clicks. 3 main things. First, its proximity. Second, its mass. And third, where it sits relative to its star, right in the habitable zone.
Goldilocks zone.
Exactly. And it's not just that it ticks these boxes, it's how well it ticks them, especially when you think about actually studying it in the future.
Okay, let's break those down. Proximity first. Less than 20 light years. You said that's basically next door, astronomically speaking. Why is that so important?
It's huge for future observation. Think about trying to take a picture or analyze the light from something incredibly faint. The closer it is, the more light, the more photons we can collect with our telescopes.
Ah, so the signal is stronger.
Much stronger. If we want to analyze its atmosphere, which is the ultimate goal here, being at 20 light years instead of, say, 100 light years makes an enormous difference. It brings it within reach of the next generation of telescopes. The feasibility just skyrockets.
Okay, that makes a lot of sense. Cuts down the challenge for the future tech. Now, the mass, nearly 4 times Earth, you mentioned that, combined with being rocky, is significant. How does that affect its potential for life? Is bigger better?
Well, up to a point, yes. A planet with 4 times Earth's mass, assuming it's rocky, has significantly stronger gravity.
Right.
And that stronger gravity is key for holding on to an atmosphere over billions of years. Earth loses some atmosphere to space. A super-Earth can cling on to a thicker, more substantial atmosphere much more easily.
So it's potentially better at keeping the conditions stable, protecting any surface water.
Exactly. Better atmospheric retention means a better chance of maintaining stable temperatures and shielding the surface from harmful stellar radiation or particle winds. It's a big plus for long-term habitability.
Okay, proximity, check. Mass and potential atmosphere, check. Now, the big one, the habitable zone. Can you define that for us again? The source mentioned liquid water.
Yeah, the astronomer Suvrath Mahadevan put it nicely. He defined it as the right distance from its star that liquid water could exist on its surface.
If it has the right atmosphere. That qualifier seems important.
It's critical. Being in the zone doesn't guarantee oceans. It just means the temperature range, based on the star's energy output, is theoretically compatible with liquid water if the atmospheric pressure is sufficient. Too thin an atmosphere, water boils away or freezes. Too thick, you might get a runaway greenhouse effect.
So the zone depends on the star, right? GJ251 is a cooler M-dwarf star. Does that mean the habitable zone is different than ours?
Absolutely. M-dwarfs are much dimmer and cooler than our G-type sun. So for a planet to receive enough warmth for liquid water, it needs to orbit much, much closer to the star.
closer than Mercury is to our sun.
Oh, often, yes. In this case, GJ 251c orbits its star every 54 days. Compare that to Earth's 365 days. It's huddled much closer to its star to get that just right temperature.
So 54 days, that's the orbital period that puts it smack in the middle of that thermal sweet spot for GJ 251.
That's what the calculations show. It's receiving the right amount of energy flux from the star to potentially allow liquid water, assuming other conditions, like that atmosphere, are met. It avoids being fried or frozen solid.
And that potential for liquid water is really the cornerstone of our search for life as we know it, isn't it? It focuses the search. Find the water, find the life, or at least the potential for it.
It's the primary driver, yes. Life, as we understand it, fundamentally requires liquid water. So finding planets in the habitable zone, especially around common stars like M dwarfs, gives us the best statistical chance. These are our prime candidates.
And you mentioned M dwarfs are the most common stars.
By far. They make up maybe 70–75% of all stars in the Milky Way. So if habitable planets can form around them, the number of potential habitats in the galaxy could be enormous.
Okay, so GJ 251c orbits this common type of star. Does it have any neighbors? Are there other planets in that system?
Yes, there is another known planet, GJ 251b. It's an inner planet, much closer to the star.
Oh, okay.
It orbits really quickly every 14 days. And actually, confirming GJ 251c, the new discovery, really depended on understanding planet B first.
I saw.
Well, the team had to use all their data, especially that long 20-year baseline, to precisely measure the gravitational pull, the wobble, caused by the known inner planet, GJ 251b. They had to perfectly account for its signal.
Sort of subtract it out.
Exactly. Only after they completely modeled and removed the effect of the 14-day planet could they confidently detect the remaining, more subtle signal, the 54-day wobble caused by the new, more massive planet, GJ 251c, further out in the habitable zone.
Wow. So finding the second planet required first getting an even better handle on the first one.
Precisely. It shows how interconnected these detections can be within a single system.
That brings us perfectly to the how. Because finding this wasn't simple. It wasn't like someone just pointed a telescope and saw it.
Well, heavens no. Not at all.
This discovery really underscores the sheer persistence needed in this field. We're talking 2 decades, over 20 years of observations from telescopes all around the world.
It's a testament to long-term scientific vision and, frankly, funding. Keeping instruments running, collecting data night after night, year after year, looking for these incredibly tiny signals.
What were they actually looking for in that data? How do you find a planet you can't see?
They use the workhorse method for finding many exoplanets, especially older discoveries. The radial velocity method, or the wobble method, as it's sometimes called.
The wobble method, okay.
It relies on gravity. Even though the star is vastly more massive, the planet's gravity still tugs on the star just a tiny bit as it orbits. It makes the star perform a little circular or elliptical dance.
So the star itself moves?
Yes. It wobbles around the common center of mass between it and the planet. It's a very small movement. For a planet like GJ 251c, we might be talking about the star moving back and forth at the speed of a slow walk, like 1 or 2 meters per second.
Okay, hold on. Measuring a star moving at walking speed from 20 light years away. How on earth do you do that? That sounds impossible.
It sounds impossible, but it's done using the Doppler effect on light. It's the same principle that makes an ambulance siren sound higher pitched when it's coming towards you and lower when it's moving away.
Okay.
As the star wobbles, it moves slightly towards us in its little dance and then slightly away from us. When it moves towards us, its light waves get compressed just a tiny bit, shifting the light towards the blue end of the spectrum.
A blue shift.
Exactly. And when it moves away, the light waves get stretched slightly, shifting towards the red end of the spectrum, a red shift.
So they're looking for these minuscule periodic shifts in the color of the starlight.
Precisely. Tiny, tiny cyclical shifts back and forth between blue and red. The timing of those shifts tells us the planet's orbital period, 54 days in this case, and the size of the shift tells us how much the star is moving, which lets us calculate the planet's minimum mass.
Wow. The precision required must be just astronomical, literally.
Absolutely exquisite. Measuring velocities of 1 meter per second requires incredibly stable instruments called spectrographs. And that's where the key piece of new technology comes into this story. The Habitable-Zone Planet Finder, or HPF.
the HPF. Right, this was led by the Penn State team.
Yes. It's a high-precision spectrograph specifically designed to achieve these meter-per-second measurements, but with a crucial focus.
What's the focus?
It operates in the near-infrared part of the spectrum. Think of it as a very complex prism that works with light frequencies just beyond what our eyes can see as red.
And it's attached to a big telescope.
A very big one. It's fixed to the Hobby-Eberly telescope at McDonald Observatory in Texas. And its name says it all. Habitable-Zone Planet Finder. It was purpose-built for exactly this kind of work, finding potentially habitable planets around nearby cool stars.
Why near-infrared? Why is that specific wavelength range so important for these cool M-dwarf stars like GJ251?
Two main reasons. First, M-dwarfs are cool, so they actually emit most of their light in the near-infrared, not visible light like our sun. So if you want the strongest possible signal from the star to analyze, you look where it's brightest.
Okay, follow the light.
Right. But the second reason is perhaps even more critical for precision. Looking in the near-infrared helps to mitigate the star's own activity, its noise.
Ah, so the starlight itself isn't perfectly steady.
Far from it, especially with M-dwarfs. They can be quite active star spots, flares. This creates signals that can mimic a planet's wobble, especially in visible light. But this stellar noise tends to be less problematic, less confusing in the near-infrared.
Interesting. So the HPF is designed not just for precision, but to look through a sort of quieter window in the star's light.
Yes, that's a great way to put it. Suvrath Mahadevan mentioned this was a specific goal. The HPF's strength is detecting these precise shifts in the near-infrared, where the star's intrinsic variability has less impact on the measurements. It helps separate the wheat from the chaff, the real planet signal from the stellar jitter.
So let's recap the detection sequence.
Yeah.
They had the 20-plus years of data from various older instruments,
Historical baseline, yes.
which helped map out the effect of the known inner planet, GJ251.
Oh.
Then they brought in the HPF, looking in that quieter near-infrared window.
Correct. They combined the long-term data with the new high-precision HPF measurements.
And once they counted for planet B.
A second, clear periodic signal popped out, a wobble repeating every 54 days. And the amplitude of that wobble, how fast the star was moving, indicated a much more massive object was responsible, something around 4 times the mass of Earth. That was GJ251c.
But they didn't stop there, did they? They wanted confirmation.
Always good practice in science. They used another cutting-edge instrument, also built by Penn State researchers, called NE.
NEID.
Yes. It's attached to a telescope at Kitt Peak National Observatory in Arizona. Now, NEID is different from HPF. It's optimized for visible light, like what our eyes see.
So they checked the signal with 2 different state-of-the-art instruments looking at different kinds of light.
Exactly. And the fact that both HPF in the near-infrared and NEID in the visible independently confirmed that same 54-day wobble gave them very high confidence that it was a real planetary signal, not some instrumental glitch or weird stellar activity.
That cross-validation must have been key.
Absolutely crucial. It demonstrated the signal was robust across different wavelengths. Corey Beard, one of the authors, really emphasized this point. They're using cutting-edge tech and cutting-edge analysis methods. It wasn't just one magic instrument, it was the synergy. 20 years of data, plus HPF's near-infrared precision, plus NEID's visible light confirmation.
That paints a picture of just how rigorous this process has to be.
Yeah.
Okay, so the signal is there, it's confirmed. But you mentioned stellar activity, the star's own noise, being a major challenge. Even with HPF looking in the near-infrared, that doesn't completely eliminate the problem, does it?
No, it mitigates it, but doesn't eliminate it. This is honestly where some of the most sophisticated work happens now. It moves beyond just building better instruments into the realm of advanced data science and computational modeling.
Fighting the noise.
Pretty much. Astronomers widely agree that disentangling the tiny planetary signal from the star's own weather is the biggest hurdle, especially for finding small, Earth-sized planets.
How does a star's weather mimic a planet? You mentioned star spots.
Right. Imagine a large, cool star spot on the surface of the star. As the star rotates, that spot comes into view, crosses the star's face, and then rotates out of view.
Okay.
That spot changes the overall light we receive from the star. It can slightly alter the measured color or brightness in a periodic way that lines up with the star's rotation period. And that periodic signal can look very similar to the Doppler shift caused by an orbiting planet.
A false positive.
Exactly. A signal that looks like a planet but is just the star itself changing. M-dwarfs, in particular, can be magnetically active, making this rotational modulation noise a serious problem. Mahat even used that great phrase, trying to find signals in a frothing magnetospheric cauldron of a star surface.
That paints a vivid picture. So how do they tell the difference? How do they know they're hearing the planet's whisper and not just the star's cauldron bubbling?
The key insight relies on color, or wavelength. Remember how the planet's gravitational wobble pulls the entire star?
Yeah, the whole star moves slightly back and forth.
Because the whole star is moving, the Doppler shift it causes should be the same regardless of what color light you look at. The shift in blue light should match the shift in red light, should match the shift in infrared light. It's achromatic, meaning colorless or independent of color.
Okay, the real wobble affects all colors equally.
But stellar activity, like star spots, is chromatic. A cool star spot emits less light, especially at certain wavelengths, so the false signal it creates might be stronger in blue light and weaker in red light, or vice versa. It depends on the temperature difference between the spot and the rest of the star.
Ah, so they can use the color information from the spectrographs like HPF and EID as a diagnostic tool.
Precisely. They use incredibly sophisticated computer models. These aren't just simple filters. They are complex algorithms, often involving machine learning.
Right.
These models analyze how the signal strength changes across all the different wavelengths the spectrograph measures. If the signal looks different in different colors, the model flags it as a likely stellar activity. If the signal is consistent across all colors achromatic, it's much more likely to be a genuine planet.
So it's not just collecting the data, it's building custom software to interpret it based on the physics of the star and the planet.
Exactly. Eric Ford at Penn State emphasized this. He said it required customizing the data science methods for the specific needs of this star in combination of instruments. It wasn't an off-the-shelf solution. They had to tailor their analysis pipeline specifically for GJ251 and the data coming from HPF and other telescopes.
Custom data science for a specific star system. What kind of complexity are we talking about? Is it like running massive simulations?
It involves complex statistical frameworks. These models have to simultaneously account for the known planet B, the suspected planet C, the star's rotation period, the typical behavior of star spots on this specific star, which they learned from the long-term data, plus the noise characteristics of each telescope used over 20 years. It's a massive computational puzzle.
That 20-year baseline must be gold for that kind of modeling.
Invaluable. It allows the models to distinguish between short-term stellar weather and the consistent long-term periodicity of a real planet's orbit. It lets them see beyond the froth to the underlying gravitational signal. This really highlights how modern astrophysics relies heavily on collaboration between observers, instrument builders, and computational scientists.
That incredible fusion of skills. Okay, so they've done the hard yards. 2 decades of data, cutting-edge instruments, bespoke data science to beat the noise. They've confirmed GJ251c. It's real. It's 4 Earth masses. It's in the habitable zone.
Yeah.
But we still can't see it, right? This is all still based on the star's wobble.
That's correct. Radial velocity is an indirect detection method. It tells us the planet is there, its orbit, its minimum mass, but it doesn't give us a picture. It doesn't directly tell us if it has an atmosphere, let alone what's in it.
Which brings us to the future. Why is this planet, detected indirectly, causing so much excitement for the next steps? Mahadevan mentioned direct imaging isn't possible now, but they're looking ahead.
Yes, and its status as a prime target comes back to that proximity. Being less than 20 light years away makes it one of the absolute best candidates we have for the next major phase, searching for atmospheric biosignatures.
Signs of life in its atmosphere.
Potentially, yes. The sources say it's one of the best shots we might have in the next 5 to 10 years to actually find chemical evidence of life beyond Earth. And its closeness is what makes that time frame plausible.
Because analyzing an atmosphere requires even more light than just detecting the wobble.
Vastly more. You need to not only detect the faint light from the planet itself, or light filtered through its atmosphere, but you need to spread that light out into a spectrum to see what chemicals are present. That requires collecting a huge number of photons. Being nearby helps enormously.
So what tech do we need for that? If current telescopes can't do it, what's coming?
We're talking about the next generation of behemoths. Specifically, the upcoming 30-meter class ground-based telescopes.
30 meters, that's huge.
Enormous. Telescopes like the European Extremely Large Telescope, the ELT, or the Giant Magellan Telescope, GMT, these represent a quantum leap in light-gathering power compared to today's best.
And these will be able to actually take a picture of GJ251c.
That's the expectation. Using highly advanced optics, including instruments called coronagraphs, which block out the overwhelming glare of the host star, they should be able to directly image nearby rocky planets like GJ 251c. It's like finally seeing the tiny firefly next to the blinding searchlight.
Okay, so step 1 is getting an image, separating the planet's light. Step 2 is analyzing that light for atmospheric composition. What are they looking for?
They're looking for the chemical fingerprints of life biosignatures. The most sought-after signs often involve what's called chemical disequilibrium.
Disequilibrium, meaning things that shouldn't exist together naturally.
Exactly. Gases in an atmosphere that would normally react with each other and disappear quickly unless something is constantly producing them. The classic example on Earth is oxygen and methane.
Right, you mentioned that. They react.
Vigorously. Oxygen wants to oxidize methane. They don't peacefully coexist in large amounts for long geological timescales without a constant source. On Earth, life provides that source. Photosynthesis pumps out oxygen, and microbes and other life forms produce methane.
So finding lots of both oxygen and methane in GJ251c's atmosphere would be a smoking gun.
It would be incredibly suggestive of a biological process. It's perhaps the most compelling biosignature pair we can currently conceive of looking for.
Are there other chemical signs they'll look for?
Oh, definitely. Ozone is a big one. Ozone forms when UV light hits oxygen, so detecting a strong ozone layer would be powerful evidence for abundant oxygen below it. Water vapor, of course, is crucial, confirming the presence of water. They might also look for gases like ammonia, which, if found alongside oxygen, would also point towards disequilibrium.
It sounds like a chemical detective story played out across light years.
That's exactly what it is. And Mahadevan mentioned his team is already working on the analytical tools and frameworks needed to interpret the data when these giant telescopes come online. Finding GJ251c gives them a specific, high-priority address to point those future instruments towards.
And this really emphasizes something important for you, the listener, to grasp. This entire endeavor, finding the planet, planning the follow-up, is incredibly resource-intensive. Corey Beard's call for community investment isn't just a side note. It's fundamental.
It's absolutely critical. These big science projects require sustained funding and collaboration over decades. Finding GJ251c is a major milestone, but it's also a justification for the next phase of investment, building the 30-meter telescopes and the complex instruments they need.
This 20-year effort, involving multiple countries, multiple telescopes, specialized instruments, custom data science, it led us to this one specific target. It really drives home that science breakthroughs aren't usually sudden flashes of inspiration.
No, they're built on decades of patient, meticulous work, often by large teams. The result is a highly validated target. We're not just guessing where to look next. We have strong evidence that GJ251c is one of the most promising places accessible to us.
Mahadevan's quote really sums it up, doesn't it? While we can't yet confirm the presence of an atmosphere or life on GJ251c, the planet represents a promising target for future exploration.
It sets the stage perfectly. The target is locked. Now the mission shifts to atmospheric characterization.
Okay, so let's try and synthesize this deep dive. We started with over 2 decades of observational data, added cutting-edge spectrographs like HPF, specifically designed for near-infrared precision around cool stars.
Combined with visible light confirmation from NEID.
Right. Then layered on sophisticated, customized data science to filter out the star's own noise by looking at how signals behaved across different colors of light. And the result, confirmation of GJ251c, a super-Earth about 4 times Earth's mass, likely rocky, orbiting right in the habitable zone of its star, and crucially, less than 20 light-years away.
It really is a remarkable convergence of technology, persistence, and analytical ingenuity. And knowing the process, knowing they spent 20 years carefully listening and filtering, gives us immense confidence that when we point those future billion-dollar telescopes, we're aiming at a target worthy of that investment.
It's validated. Okay, so let's leave you, our listener, with a final thought to chew on. It took all this effort, 2 decades, multiple international teams, bespoke instruments, advanced computation, just to find GJ251c and confirm its basic properties, establishing it as a prime target.
Just to get to the starting line for the really interesting part.
Exactly. So given that immense effort just to identify where to look, what does that tell us about the scale, the patience, the sheer generational commitment and investment required for the next phase, actually analyzing that atmosphere and searching for those faint chemical hints of life? What does it take to find that first definitive biosignature?
It really reframes the challenge, doesn't it? If filtering the star's noise to find the planet was this computationally intensive, imagine the analytical effort needed when we start getting detailed atmospheric spectra back from these future giants. It suggests the search for life is going to be as much about breakthroughs in data science and AI as it is about building bigger telescopes. The computational astrophysicist is truly at the forefront now.